This is a lesson on properties of waves in the simple harmonic motion in waves unit. To begin with, I want to just talk about what a wave is defined as. A wave is defined as a disturbance that propagates from where it is created. And for me, this is the most major property of a wave, is that it carries energy from point A, your source, to point B, a receiver, without a transfer of matter between the two. It's energy transfer through some sort of medium, but that medium does not move. It only transfers the wave. Through this medium, the wave moves with wave velocity, and I've called it V sub W to denote velocity of wave. A wave can be a single pulse of any shape. You could have a square wave, a triangle wave, you could have any sort of wave shape. But what we're going to note is that all waves have a wavelength. How long or wide is that wave? And you can see I put a couple of examples over here. Here's a wave up here that's just a single pulse, and you can see that it has a wavelength. How long is that wave? And it moves through time. The medium will move up and then fall back down. The medium does not move, only the wave moves. You can see that also down here with the slinky. Whether I compress the slinky horizontally and the coils compress and stretch in the horizontal direction, there will be a wavelength. Or if it's oscillated up and down, maybe it's easier to see a wavelength in that way. Notice that the whole slinky does not move. The wave moves along the slinky with a wave speed, but the particles of the wave stay near where they are, right? If it's moved up and down, this piece of slinky just moves up and down. If you have a wave that oscillates horizontally, this piece of slinky moves back and forth right there. It doesn't move down the slinky. It stays right in that area, okay? The thing about waves and why it's in this unit is that repetitive waves are an example of simple harmonic motion. So when you look at properties of simple harmonic motion, which I had covered in a prior lesson, waves also have these properties. This includes amplitude, period, frequency, and angular frequency. Remember that omega is 2 pi times the frequency, and the frequency is 1 over the period. So you get this relationship between omega and the period. So this is true for waves as well. When we look at wave motion, I've defined the velocity of the wave. The velocity of the wave is how fast those pulses move down the medium. It's the direction of energy propagation. Remember, waves propagate energy, and it's moving from one source to the other. And so the direction of the wave speed, V wave, is in the direction of the energy propagation from point A to point B. And you can see that up here with the slinky. And this is a slinky in both situations. An important distinction among waves is the direction of displacement of the medium carrying the wave. And you saw this on the prior slide. I can cause the matter to move perpendicular to that velocity of the wave, or I can cause it to move parallel to the velocity of the wave. And that's how we get the two distinctions. Transverse is when the displacement is perpendicular to the direction of propagation, and longitudinal is when the displacement is parallel to the direction of propagation. And a few terms that come in here is compressions and rarefications. So when I look at this slinky here, I can see that there's some compressions in here. There's those compressions. And then the rarefications is where it gets spread out. So those are the rarefications. Those are a few vocab terms that you will be expected to know as we move forward in waves, and it's a very important property of waves as we move into other sorts of waves such as light waves. The wave speed is fairly easy to calculate. We think about how far has the wave moved in a certain amount of time, right? Velocity equals distance over time. And when I write that out, we can get the distance over a certain amount of time, which is the period. It moves actually the wavelength of the wave, which I denote. It's denoted with lambda. and over the period. So we get lambda over the period. Remember, the period is 1 over the frequency, so you can see that this equation down here falls out very easily from constant velocity. It has a constant speed, distance over time, and we get it related to the wavelength and the frequency of that wave. And this is true for all waves regardless of the medium or lack thereof if we're thinking about light. The speed of the wave depends on the properties of the medium carrying the wave. So if you think about sound wave travels at different speeds in solids or liquids or in air, right? Another type of wave we will be looking at is a wave on a string, and you can imagine that the properties of that string contributes to how fast that wave moves along a string, such as in musical instruments. So we will be using this equation frequently with waves, and I've chosen a series of problems to get used to using this equation and thinking about properties of waves and identifying different quantities from waves. The first is mosquito's buzz. A mosquito flaps its wings 600 vibrations per second, that's a lot, which produces the annoying 600 hertz buzz. That's what you hear. How far does the sound travel between wing beats? In other words, find the wavelength of the mosquito's sound. Assume the speed of sound is 343 meters per second in air. So they give us the velocity of the wave, that's the velocity of the wave. The speed of the sound is the velocity of the wave. We're asked to find the wavelength, and we give the frequency. Remember, frequency is given in hertz, and we're given the frequency. So the wavelength is going to be the velocity of the wave divided by the frequency. So I will take the 343 meters per second, divide by the frequency, which is 600 cycles per second, and I'm left with meters overall. When I run this through the calculator, I get 0.5716 repeating meters, which is about 57.2 centimeters. And that's how far the sound travels the flaps of a mosquito's wings, almost 60 centimeters. So that's a basic application of the equation here. I chose another one that's a little bit more involved. They give us different information. It says tsunamis are fast-moving waves often generated by underwater earthquakes. So we're thinking about water on the ocean. It gets shifted up and maybe a pulse goes traveling across the ocean. In the deep ocean, their amplitude is barely noticeable, but upon reaching the shore, they can rise up to astonishing height of 6 stories. One tsunami, generated off the Aleutian Islands in Alaska, had a wavelength of 750 kilometers. So I'll write that down. Lambda is 750 kilometers. And I am going to put that in meters here, multiply by 1,000 in order to get it to meters. And traveled a distance of 3,700 kilometers in 5.3 hours. What is the speed of the wave? Find the wave's frequency and period. So if I wanted to find the speed of the wave, I would need lambda and the frequency, but I only have lambda, so I can't find the speed that way. But for part A, I can go back to what I know about constant velocity. Velocity, the wave travels 3,700 kilometers, and I'm going to convert this to meters. I'm going to add 3 more zeros to get it to meters, in 5.3 hours. So I'm going to take 5.3 hours and then multiply by 3,600 in order to get it to seconds. So you can see that some factors of zero cancel here, and when I find the speed of this wave as it travels across the ocean, it's 2.8 kilometers, but when I run it through the calculator, the number for meters per second is 277.7 repeating meters per second. So that's the speed of the wave. So it's about 2.8 kilometers per second. That's pretty fast. It's traveling pretty fast there. It's a good clip. 3,700 kilometers in 5.3 hours. So if that wave was traveling towards you and you were given a notice to clear your home, if you lived near the beach of the ocean, that's why you have that much time to clear out, because this wave is really traveling. Now that I know the velocity of the wave, I can relate it to the frequency. It says find the frequency in the period. So the frequency of the wave is going to be the velocity of the wave divided by the wavelength. And so I have the velocity of the wave, 277.7 repeating meters per second. I divide by the wavelength. Well, I converted that to meters already. So that's 750,000 meters. So I get 1 over seconds overall with my units when they cancel out. I have meters per second on top and meters on the bottom, so I end up 1 over seconds. And so the frequency ends up being a really small number, right? I'm dividing by a large number, so that's 3.70, and that number repeating. So I'm just going to put that times 10 to the negative 4th hertz. Now that I found the frequency, the period is just 1 over the frequency. So I'll go 1 over 3.70 times 10 to the negative 4th. So we're going to see how long it takes for that wave to have a wavelength, right? How long is the wavelength of that wave? What is its period? So when I calculate this number, I get 2,700 seconds. Exactly. Kind of weird, but that's what it is. And I divided by 60 to figure out how many minutes this is. And the wave has a period of 45 minutes. So it's a pretty long wave when I think about how long the wave is. It does not oscillate up and down very fast at all. The last problem I've chosen for us is the vibrating string. It says the speed of a transverse wave on a string is 450 meters per second. So that's V wave. That's this thing. And the wavelength is 0.18 meters. So I have the wavelength. I could find the frequency right away. It says the amplitude of the wave is 2 millimeters. How much time is required for a small section of the string to move through a total distance of 1 kilometer? Well, they give me the amplitude here, and when I think about a transverse wave, remember this is a wave that oscillates perpendicular to the direction of propagation. So it's oscillating up and down, and the wave is moving in this direction. The wave oscillates up and down in this direction. It may make sense to you that if this is 2 millimeters here and 2 millimeters down here, in one cycle, it will travel 8 millimeters total, up and down. Remember that part of the string does not move along with the wave. It moves only up and down with a transverse wave. So in one cycle, it will move up and down, 4 millimeters up, 4 millimeters down, so 8 millimeters total. It says, how long does it take for it to go up and down for a total of 1,000 meters? That total distance is 1,000 meters. Well, it seems like if I need time, I have to relate it to maybe the period, right? One cycle has a time, which is the period. And I can calculate that. The frequency is 1 over the period. So if I want to find the period, let's see, the frequency, I can plug that into the equation. V wave equals lambda divided by the period. I'm going to solve for the period. The period equals lambda divided by the velocity of the wave. So I can plug numbers in there. 0.18, right? The wavelength over here is 0.18 meters. The velocity of the wave, they give me 450 meters per second. So I have meters over meters per second, and notice that gives me seconds, and I get the period of the wave to be 4 times 10 to the negative 4th seconds, which I expected it to be really small. It's a really fast wave, and the amplitude is really tiny, 2 millimeters. It's a string. So now that I have the period, I'm going to figure out how long does it take. So I will convert. I'm going to do sort of like unit conversion here. I'm going to start out with 1,000 meters. That's how far I want to go. And I know that it will take one cycle takes 8 millimeters. And so that kind of tells me how many cycles it will take in order to cover 1,000 meters. Now I know I need to change from 1,000 millimeters to 1 meter, and that will help me get to the right units, right? My meters cancel here and my millimeters cancel here, and I'm left with cycles. So this is going to tell me how many cycles it will take to get 1,000 meters. What I'm also going to multiply in here is the time. One cycle, I know, is this many seconds. 4 times 10 to the negative 4th seconds. And notice the cycles cancel here and here, and I'm left with cycles in units overall. So I'm going to take 1,000 and multiply it by 1,000 and multiply by 4 times 10 to the negative 4th and divide by 8, and that will give me the amount of time. So when I run this through the calculator, I get a nice round 50 seconds.